Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to talk about calorimetry. And really the importance of calorimetry is this is how we can detect heat transfers. Because again, we know that if I transfer or move energy, I should watch the temperature increase or decrease. But here's the issue. How am I actually going to physically set that up? And so what we're doing is making use of calorimetry to lock two particular transformations inside a single isolated system. So that way, if I can measure a change in temperature of one substance, I should be able to determine how much energy came from the other part. And so we can do this making use of the first law of thermodynamics. If both of these the system and the surrounding are trapped in an isolated system, the change in energy should be zero. So one of the ways you can imagine doing something like this is, let's say I heat up lead, I go ahead and I put it in water. If no energy is allowed to enter or exit, any of the excess energy that was trapped in that hot lead is going to immediately go in the water around it. So the water should increase in temperature while the lead decreases. And this is again based on this basic principle. Any change in energy of my system, in this case lead, has to be offset by the surroundings, in this case water. And so if the system goes down, so lead cools, negative internal energy, then the water heats up, positive internal energy. However, it is worth noting that sometimes you'll do this transformation not under isochoric conditions, where we're going to be using internal energies. Sometimes you'll be doing it under isobaric conditions. So if the pressure is being held constant instead, you can do this whole same process, except with enthalpies. So again, enthalpy of the system equals negative enthalpy of the surroundings. And this sign convention is going to be very important because if one substance cools, the other heats up, and vice versa. So the simplest form of calorimetry simply is this idea of I add a hot substance to a cold substance, or a cold substance to a hot substance. Typically, we use water as one of our substances, mostly because it is very cheap, secondly, because it is very available, and third, because it is very well known. Everybody knows the heat capacity of water. And so it makes a good reference condition. So what we can then do is, if I know the mass of my first substance that I'm adding and its heat capacity and its change in temperature, this should be equivalent to that of water. So again, it's going to be very important that you know exactly how much water is present. We know its heat capacity, and it's fairly easy to measure the temperature change. So usually then we're trying to determine one of the three things about the substance we're adding to water. Either its initial or final temperature, most commonly initial. Most frequently it's heat capacity, or occasionally you can use this to determine exactly how much substance you added. If you know its temperature and its heat capacity, well, you can back out exactly how much of it you had. So again, typically we're going to be doing this with a good method of determining heat capacities of an unknown substance. So for example, let's go ahead and do this with lead. So let's imagine that I heat up 150 grams of lead to 100 degrees C using boiling water. So I then go ahead and place that lead in 50 grams of 22-degree water. Now I measure the final temperature to be 28 degrees. So we're going to use the heat capacity of water of 4.1813. So again, joules per grams Kelvin. And always make sure you watch your units when playing with this. So because we're working with grams, that means I'm looking at specific heat capacities. And I'm going to try and determine the specific heat capacity of lead, not its molar heat capacity. So doing this, I'm going to set up the mass of lead times the specific heat capacity of lead times the change in temperature equals the negative of the same thing for water. So then we're trying to solve for heat capacity, so you can rearrange the equation. So it'll be our water terms divided by the mass times change in temperature in lead. So let's go ahead and walk through each of these terms individually. So we know that we've got 50 grams of water. We know its heat capacity. Now the tricky one is the temperature. We know we started at 28 and we're decreasing. We ended at 28.8 and we start at 22. So final minus initial. Always make sure you do final minus initial. So in this case, you may note that the units are in Kelvin, but I used Celsius because if I was going to convert the Celsius temperature to Kelvin, I'd do so by adding 273.15 to both my final and my initial temperature, which would cancel out. So I have previously said, always use Kelvin. The one exception is when we're looking at changes in temperature. We do get a free pass here. So then for the denominator, I've got 150 grams of lead, and my final temperature is 28.8, and my initial temperature is 100. So I can go ahead and plug in all these numbers, and lo and behold, we have the specific heat capacity of lead of about 0.133 joules per gram Kelvin. And it is worth noting that a lot of our specific heat capacities are going to go in between these kind of two regimes. Water is one of the higher specific heat capacities, and most of the metals end up being fairly along these lines. So one of the things that we're going to be looking at is which substances have higher heat capacities. So the higher the heat capacity, this means I have to put in more energy to make the system have more translational motion, because if you remember from gases, that's really what we're measuring when we're measuring T. So temperature is literally how much translational motion I have. Now, if I've got something like a very light molecule like water, it tends to have very high specific heat capacities because remember, this is energy per gram. And 1 gram of water has a whole lot more molecules to move around than say 1 mole of lead, which is fairly heavy. So in general, lighter molecules tend to have higher specific heat capacities. In contrast, if I'm looking at molar heat capacities, so the amount of energy it takes to heat 1 mole, it tends to flip. Larger molecules tend to have a lot more types of movement they can do. They have more rotations, they have more vibrations, they have more ways to get jiggy with it. So it takes more to get them running around instead of just dancing in place. So again, always watch out for whether we're talking about specific or molar heat capacities. Also, in general, whether you're looking at specific or molar heat capacities, one of the things I do like to emphasize is liquids tend to have very high heat capacities because liquids like hanging out with each other and they can move around each other. And this gives them a lot more movement than you're going to have in a solid, which will heat up fairly quickly, and gases, which just don't have that much substance to move. So in general, if you want something with a high heat capacity, you typically go towards a liquid. Then it's typically a solid, and lowest tends to be, in general, gases. But as you can see by this table of heat capacities, there's a lot of room for flexibility. So next time, we're going to be using our knowledge of changes of heat to just look a little bit more specifically at how we can use this to figure out the heat generated by chemical reactions. Until then, take care.